algebraic approach to valuation, right? To get certain convex body attached to semigroup or any algebra or graded algebra. So today, this week, we will focus on geometric side of Newton-Okounkov body theory. Okay. So the geometric valuation, roughly speaking, is the Lazarsfeld and Mustata's approach. So you should understand the Newton-Okounkov body theory as a certain tool to study your object. So it's very flexible. Right? So Lazarsfeld Mustata wanted to study these line bundles on a variety. So here's the setting. So X is a complex projective smooth algebraic variety of dimension n. And now we fix a flag of sub-varieties of X. Namely, so the first one is X, it goes Y1, Yn, and the last one it will be just a point such that the codimension of yi in X is I, so the dimension goes down by 1, and all yi are irreducible, and it's smooth at the point Yn. Okay, so any flag of subvarieties of X satisfying this condition is called admissible flag. Okay. Now let's choose an effective divisor on X. So it is a formal sum of finite many prime divisors. So let's do with the example. So say, so example 1, so say X is a curve, complex curve. Then flag means, admissible flag means nothing but choosing a point. Okay? So say X and a point, let me denote it by P naught. So P naught is a smooth point. Yeah, non-negative. Non-negative. Yes, so it's a finite formal sum of prime divisors say nz times z, so it's a finite sum such that nz are positive, non-negative integers. So just note that we restrict to this smooth algebraic variety. So, well, if you are not familiar with the divisor theory, don't worry about it. So this is nothing but the formal sum of this sort of hypersurface. However, if you get rid of the smoothness, then we goes to a Cartier divisor. So still we can generalize. Okay. But so for now, you can just consider that way. So effective divisor in this case is nothing but a formal sum of finite and many points, right? So how, okay, so say that's the m p dot p. So p is a point. Okay, finite. Nice sum. Can understand that way. Okay. So this is the setting. So we want to define an assignment of this effective divisor.
Such an divisible flag always exists.
Yes. So, well, it's a smooth variety, right? So you can take smooth hypersurfaces. Yeah. Even if it's not smooth, so you should think the non-singularity is generic. So you can always find a non-singular variety in situations. Yes, this is always. Actually, yeah.
In that case, I think the yn must be smooth point.
So here's this pt is not necessarily. Oh, in this case, yes, this is a smooth point for y naught. I did not assume that each yi is non-singular subvariety. I did not say that. So these intermediate varieties may have singular points, but this fixed point should be smooth point at that smaller subvariety. So if you want to make everything clear, you can say all the subvarieties are non-singular. That's also okay. Yeah. Okay. So now we want to assign n integers attached to E with respect to the flag of this admissible flag. We just want to attach n integers to this effective divisor with respect to this flag. So for example here, what would it be? So any guess? We have a formal sum of this bunch of points, and we want to get a certain integer of E with respect to this flag. So flag is not going to be fixed a point. So it's nothing but the coefficient. Natural choice, natural definition will be the coefficient of P naught in E. So in Ben's language, this is vanishing order of this effective divisor along the point P naught. When I say order of vanish, I look at this one as a Cartier divisor. So Cartier divisor means locally E can be understood as the zero locus of a certain function locally. So E can be represented as a zero locus of function, and then this is the order of that function at the point. Okay, let's do one more time. So number 2. So say x is the simplest one, C2. Yeah, and let me choose the flag this way.
In case E may miss the point.
0.
No, E is some finite points, right? So E may not contain P0.
Right, which means the coefficient is 0. So then in that case it's 0. If P naught does not appear, it means the coefficient is 0. It means it does not vanish at that point. Yeah. So now let's choose flag of admissible flag. namely the natural coordinate system, right? So C2 and the zero locus of x, namely the y-axis, and the origin, x, y dimensions. My notation follows the Harshun's book. Okay, so now let's say effective divisor. Let me choose this. So it's the zero locus of x squared times y cubed. So this one can be written as the formal sum, right? So 2 times v of x plus 3 times v of y. To make it extremely precise, what I mean, this is an effective divisor, and I denote this one as some divisor class here. So usually we put the class, but is everyone okay here?
So that means that this is the zero set of x squared times y cubed.
Right, and we record the multiplicity.
This consists of x equals 0, y equals 0, but it has a order of multiplicity 2 and 3.
Yes. Okay. Now, so v1, so so now, okay, let me just to make the notation simple. So say what is the v1 of e? I mean, the first one, right? So we need 2 integers attached to e. So the first one will be the order of e along y1. So that's the same thing. So the vanishing order of e along the first hypersurface, which is 2. So if I try to, so we have a C2. Now we have a flag, right? Everything and this y-axis and the origin. That's the flag. And now our effective divisor is the union of these 2 axes. And this one has a multiplicity 2, this one has a multiplicity 3. So those are thick lines. So the first V1 record the order of vanishing of E along the first hypersurface.
Like
yes. Yeah. So define the following way. So V1 is order of E along Y1. Or you can think this way. This is the coefficient of y1 in E. Several way, right? You look at this, because y1 is irreducible variety, y1 can be here. So, okay. Now what is V2? Okay. So V2 obviously has to do with this origin. So if you just restrict E to the origin, it obviously just vanishes because it contains this one. So we have to subtract this one. So this order, but so we restrict to this codimension 1. So E minus 2 times V of X, which is the remaining part. And now you restrict this one into Y1. So now this one is in this one-dimensional one, and now you take the order of the vanishing order of this one along y2. So that will be in this case 3. Okay. So let me just write it precisely. So let E1 as E minus V1, Y1. So that's another effective divisor on X. But now we restrict this one onto Y1. Okay. So now we consider this one as effective divisor on Y1. So V2 will be order of vanishing of E1 along Y2. Okay.
So Y1 here is Y.
So this is yes.
Y is Y-axis.
This is Y-axis. This is the origin.
Right.
This one is the zero. Is the points where X vanishes. So the zero.
E1 minus. If we are restricting this divisor to Y1.
You can think this way. So this, okay. E is locally defined by this along Y1. So order of vanishing will be 2. Now subtracting means you divide this. So now Y cubed, but also this is well defined.
Okay.
You restrict along Y1 and yes. Well, so I just want to note that in this case, the 2, 3s are nothing but these exponents, right? And this thing happens, which means you didn't really have to do all these restrictions, right? You could just look at the order of vanishing along this. That's just because this flags has something to do with this simple normal crossings. Okay, when it comes up, I will tell you. So, okay. Okay, so that's how you define an integers inductively attach it to this effective divisor. So now we consider a certain collection of effective divisors coming from a given line bundle. Line bundle L on X. So first of all, any line bundle on a smooth projective variety is coming from a Cartier divisor D. So if you read Lazarsfeld and Mustata's paper, they start from a big divisor, and the line bundle coming from that big divisor is called the big line bundle. So yes, okay. They wanted to study certain volume function of these divisors, so they restrict to this big divisor. Okay, so what do we do? Okay.
저기 effective divisor coming from a given line bundle.
Yeah.
That means you have a line bundle, and then you consider this divisor as a zero set of a certain section.
Yes, that's what I'm trying to. Yes, this is just a rough outline of what I will do. Yes. So what we do is that, so line bundle, you consider this. Let me just write down all of it, okay? So this is the space of global sections of line bundle L. Just keep interchanging these two. So if you have a section here, there is effective divisor. So this is the divisor of the zeros of sections S. This is an effective divisor. Linearly equivalent to D. So in this divisor theory, there are three notions: divisors, line bundle, and invertible sheaf. So these three notions are identified and interchanged. So I began I gave you the definition of this V.
Fully one-dimensional sheaf.
Invertible sheaf is locally isomorphic to O.
So
Yes.
That's a one-dimensional.
Yes. So invertible sheaf. So if you have a line bundle, you consider all the sections of the line bundle. It's an invertible sheaf. So. So, but then I will focus on the line bundle approach so that you are not so confused. Okay, so now, let's define V y naught of S as this V y naught of this effective divisor. This is just different point of view. When you see a certain algebraic variety or things, will you see this one as the zero locus of an equation? Or that set itself. Okay, so far I defined the following. I defined this valuation on this space. So this is a finite dimensional vector space because X is a projective variety. So it's L minus 0 to Zn. N is the dimension of our variety X. Okay. So now so there, implicitly what you are considering is this following algebra, so A of D. So this is the direct sum of if you want to record the grading of AD, you can put like this. So this is, okay, to make it super precise, there's identification from this space to this so this is the invertible sheaf of sections of this line bundle, and then this space is all the rational functions non-zero such that the divisor of F plus D is non-negative. So this is actually this zero locus, the divisor of zeros of the global section can be written as like this. Comes from one rational function. So there is just identification between this space then this one is subalgebra of K of x. So that is the field with the transcendental degree n with the polynomial, the variable t. Well, so that is the algebra we are considering, right? So the semi-group we are getting is this M Vy not S, such that S is non-zero and it's the global sections of the line bundle coming from M times D. Well, that is nothing but the tensor product of the line bundle. So last time said, so if D is M-line bundle, this is the algebra of integral type. If D is any divisor or L is any line bundle, this is algebra of almost integral type. So now it depends on what you want to do. Sometimes you don't take all this space. You may take a subspace of this. And you will get another Newton-Okounkov body as well. So the Newton-Okounkov body, the Newton-Okounkov body of this semi-group is we denote, or we say this is the Newton-Okounkov body of our algebraic variety with a given choice of line bundle and a given choice of this flag of subvarieties, admissible flag. By the way, so this valuation has one-dimensional leaves, and the proof is in a Lazarus-Fehl-Mustata lemma 1.3. This is simple, but it uses divisor theory. Let's do more examples.
Since I do not know very well about this divisors theory, okay, you have a line bundle, and then you have a section, and you can define an effective divisor as the zero set sections. But here you have a divisor, and then divisor, effective divisor corresponds to a line bundle. But divisor is associated from line bundle and the section, then you get divisor. But from a divisor.
So you can start from a line bundle. So suppose you have a line bundle. Actually, you really don't have to talk about that D. I just chose a divisor D whose corresponding line bundle is actually L. But you don't really have to say that. If you have given line bundle, you construct the valuation. Yes. So you can just forget about this D.
Yeah, but my question is, I'm just asking you not this one, not the valuation, but about the devices. So you have a line bundle, then you can, and the section there,
Yes.
then you can find the divisor, right?
Yeah, so this one is one of them. Yes.
Yeah. But you can, if you choose different sections, you get different
Divisors, but you get still the same line bundle, isomorphic to each
from the
other.
same, from line bundle. So line bundle is given, and then section is given there.
Which section?
From line
You
bundle.
choose.
Yeah, you choose if
Uh-huh.
if a line bundle is given and the section is given, then this defines a divisor. Effective
Yes,
divisor,
yes,
right?
yes.
If you have a divisor, then can you associate a line bundle?
Yes.
Yeah, but you also have to have a section on there, right?
Yes.
So this correspondence is not, I mean, you have a line bundle plus sections defines divisor, but I mean, whenever I listen to this, you have a divisor, and then just simply associate line bundle. I don't see this.
Yes, so yes. So here's the thing. If you have a line bundle, you can think about lots of divisors coming
Right,
from
right.
the sections. They are all linearly equivalent to each other.
So what is a linearly? Could you remind me of that?
Sure. So
So when you are talking about divisor, you are bonding out by equivalence relations, by linear equivalence.
yes. So that is divide. S is divisor of F plus D for some rational functions.
So up to the equivalence, you can associate
Yes. Yeah.
line bundle. Given a divisor, you can associate.
Yes. So you can just if you want to look at this convex body as invariant of line bundle, you don't really have to single out a 1D, right? You don't have to actually. But if you want to study your own divisor, that's how I guess. Yeah.
But can you just associate from a line bundle
Yes.
without divisor? Can you?
Yes, actually, yeah. Right, you just say that L, then, well, this one is just, you can just say that these are just effective divisors, right? And you define like that. It just has nothing wrong with this map. Yes. Let me think why, yes. Hope that I didn't miss anything. Yes. Okay. Let's erase this one. We want to see two cases which show that the semigroup coming from, sorry, you can say L, but for me, I really want to single out certain line bond, a divisor, which shows that the semigroup S of D depends on the choice of flag. Okay, so here is the general setting. So X is an elliptic curve. This is the most famous one.
But definition is quite obvious that this is depending on the choice of flag.
Of course, but some people don't write it. They just write down like this. The choice is hidden. So this also is about what you really want to say. So there is a one invariant attached to Newton-Okounkov body, which is independent of the choice of this flag, nothing but the volume.
What about divisor? Is this depending on the choice of divisor? Or?
Of course. So this all up to the linear equivalence. So it depends on the choice of
Up to the
right. So the Newton-Okounkov body is an invariant of a line bundle. If you want, you can think this way. Yes.
So if you choose different divisor from the same line, then how different is the Newton-Okounkov body?
It's the same.
Translation was just
No, this is the same. I mean, yeah.
So actually,
Given flag of variety, yes.
so the D is not necessary actually.
Right. But if you want to sort of like construct a certain example, then you start from a D. That's why.
Right. Yeah, it's going to be easier.
It's like a choice of coordinate system. Depends on this D. So the initial goal was to describe this volume of divisor, which has a definition, mathematical definition, or in certain case is the degree of this embedding. They wanted to describe this numeric invariant as a volume of something, right? And then this Newton-Okounkov body gives the answer. So in that statement, you really don't have to worry about the choice of flag. But now it's a very natural question. How is it controlled by the choice of valuations, right? So here you go on. So say x is an elliptic curve with a given point. So let me just denote it by P naught. So elliptic curve, so this is complex curve with a genus 1, or you can think it's a Riemann surface with a genus 1, or donut. And let me choose a divisor, which is a 3 times P naught. So it's effective divisor. This divisor is very ample, which means provides an embedding of embedding of the elliptic curve. So x is embedded into this. Okay. Let's slow down. So H naught x. Okay. So some people put the line bundle corresponding to 3p naught, or just put 3p naught. So this is a finite dimension vector space. Actually, this one has dimension 3. Take the dual vector space and projectivize it. So this is a Kodaira embedding. So if you choose a basis of this vector space, you can say that is P2. So it's the embedded one is the curve with the degree 3. It's the famous one. So what happened is in P2, x is embedded into P2, which is defined by this homogeneous polynomial of degree 3. So the embedded one, this plane curve has degree 3, and this given point is a certain inflection point. So my picture just shows that the embedded version of x. Actually, there are only finite many inflection points, and P naught is one of them, which means the tangent line of x at P naught has intersection multiplicity with the x3. So that's the real picture, a fine real picture of elliptic curve embedded in P2 using this fixed line bundle or divisor.
So that P0 is very ample. Is it a well-known fact?
It's because it has degree 3. Yes.
So every degree 3 divisor is very ample.
For elliptic curves, so yes, it's about the Riemann-Roch theorem. So it's all about the dimension of this space. Yes. So this example requires some curve theory. So here, so if x is a curve, smooth curve, if you want, and this is a divisor, then the dimension, we usually use this notation, dimension of the big H naught. Okay, so x of d is same as degree of d plus 1 minus genus of x. Sorry, so I really need a smooth because I'm using. So degree means d is a divisor, so it's a formal sum of point. Yeah. So the degree of d is nothing but the sum of these all coefficients. Okay. So for us, what is it? So for us, degree d plus 1 minus g. So degree of d is 3 plus 1. Genus is 1, so it has dimension 3. There are more criteria for a very ample line bundle, but still, so it's big enough. Okay. So that's the situation here. Okay. So we have x and we have a line bundle or a given divisor d. Now, first case, so let's choose flag, admissible flag. So here, because x is a curve again, choosing admissible flag is nothing but choosing one point. So well, let's just choose that point, that special point P naught. Okay, so let's choose that as the flag, admissible flag. Okay. Okay, now we are considering all the effective divisors linearly equivalent to D, these 3 P naught. Please remember our X and D is fixed. Okay? We want to find the invariant of D up to equivalent, linear equivalence. So we want to find the values of effective divisor linearly equivalent to 3P0. And an effective divisor is linearly equivalent to 3P0 if and only if E is the formal sum of 3 points which are collinear. We are just doing curve, okay? Divisors are nothing but the sum of points. Actually, here it's not really just a formal sum, because the elliptic curve has a group structure. So for me, that plus is so. So collinear means, okay, 3P naught is embedded into projective space. So that is sort of, you can consider this as the hyperplane section, which means you get into X and you consider intersection with any line in P2. Then you get these 3 points. Collinear means it's a hyperplane section. So there are P, Q, R. This effective divisor is always linearly equivalent to 3 P naught. Okay. Okay. They are not necessarily distinct. Right? So for example, also say, okay, the first case, say, let's take that L1 as the tangent line. Right? So let me use that. So E is 3 P naught. It's already effective divisor, linearly equivalent to 3 P naught. So the valuation of E is 3. Right? So what is the valuation? So the valuation of E is the order of vanishing of E along that given point, which is 3. But also we can have this PQR. Yeah. So let's find, suppose I have a line passing through P naught. Just transversal intersection. So then E is P naught plus Q plus R, which are not equal to P naught. They are not equal to P naught. Then valuation of E is 1. Of course, we can have E, P, Q, R. These are all, so P naught does not appearing. Then V of E is 0. And please, we cannot have E is 2P plus Q. 2P naught, right? It means there is a line which is tangent to P naught intersect with another point, and that's impossible because P naught is inflection point. So you cannot have 2. Well, we just consider these 3 cases, but please remember V has one-dimensional leaves, so the number of these, okay, L, let me just use the notation, okay, so the minus 0 is the dimension of H naught, right? So it's 0, which we already know. We already got 3 points. So we found all the values on the first level. I only considered this first level. So this one is the axis which records the levels. And the first level we have 0, 1, we don't have 2, we have 3. In the second level, you can think about what it means. There is a section which has 1, 0, 3 values, and if you multiply 2 sections having 1 and 3, then the second level you will have a value 4. Yeah, so keep going. But anyway, so you will have the cone goes like this. So it's finite generated. Finite generated by level 1. And when you cut by this level 1 hyperplane, you get the Newton-Okounkov body. But actually, note that, I will talk about that one later. Okay, so this closed interval is the Newton-Okounkov body. But actually, we already know the Newton-Okounkov body for a curve because we know the degree. So the degree of the Newton-Okounkov body of curve, so this is curve, right? And we have this 3p. P naught, and whatever the any flag. So always the closed interval 0 and 3, because we know the degree of x in this embedding is 3. So the volume, okay, the Newton-Okounkov body is nothing but closed interval, one-dimensional convex body. So it's an interval, and must have degree. It must have volume 3, so length 3, integer length, and starting from 3, 0. It should be. So actually, it's all about semi-group. So you have to distinguish these two data, the semi-group and the Newton-Okounkov body. So as you may see, it will be very, very, well, actually we cannot, in this case we know what is the semi-group, right? Because it's a finite generated by level 1. We know what is the whole, we know the whole picture of a semi-group, but in general, to find the semi-group, it's infinite many steps. But from a certain extra information, we know the Newton-Okounkov body. So if we know the degree, you don't really have to do all this computation. Okay, let's consider another.
So what is the semi-group then?
Also, yes. So
in this case, any flag.
For any flag.
Yeah, here this is the flag, this particular flag.
Yeah, let me show you another one. Okay. Yeah, any flag. Yes. So
this is an example which shows that the Newton-Okounkov body's volume is independent of the choice of y0, but still the semi-group is
yes, I think I reversed the choice. So just okay, what I'm saying, to find the Newton-Okounkov body for this case, you don't have to do that, right? Because we already know Newton-Okounkov body is in a closed interval with length 3. It should be just.
That's the result.
So, but yes, and then let's find out another generic point. And okay, so now the second case. So x and any other point. So let's say p. So p is a generic, which means not inflection point. Okay, there are only finite many inflection points. So if you just choose randomly, you don't get inflection points. So let's say, well, okay, just forget then. That's p.
So we use this p0 as an inflection point.
Yes.
The place where E does not have 2p0 plus q.
Right. Yes.
That's because p0 is an inflection point.
P0 is so when you say my understanding about this terminology elliptic curve, it must always come with a fixed point, which will act as the identity of this group structure. Otherwise, you will just say curve of genus 1. And so when you say elliptic curve, I think it has something to do with the number theory or this group structure.
So you choose
I chose from the very beginning.
From the embedding, this p0 becomes the
inflection point.
The inflection point is the identity of the group structure.
Yes, yes, yes. So now we choose any other point to have this flag. Yeah, let's keep doing. Okay, this is not, this one is still like this, okay? So, okay. Well, the first one gives us 0, right? So say E is, we don't really need that. Well, so first case, if E is 3p0, then the valuation of E with respect to P is 0. Then the coefficient of P appearing in E is 0. Okay. And now, okay, what else? we may have a line passing through P. Okay. If you want, you can use some color. So this is another P fixed. P plus something else. And the valuation of P is 1. Well, one of them could be P naught. You don't care. And now you can have 2P plus something. You just take the tangent line. Of course, you cannot have 3 times P. So cannot have, because this is it. Okay. Because P is not an inflection point. Okay. Again, we got all 3 values we are looking for. So from this, we know the first level of the semigroup. So this the first level of the semigroup. So says that that's S1, okay? So it's 0, 1, 2. Well, before going into the second level, actually, that requires curve theory. Second level and third, we already know what is this cone, the closed cone, because we already know the convex body should be this. It should be like that. So what it means is that you have a certain point, but not hitting. Right. So here's the curve theory. So when P is a generic point, you can always have these values. You can achieve all these values consecutively. And up to what? Up to, so let's say that depends on this dimension. Let's do this one. So level M is about the, okay, what I'm saying is the number of values we are looking for is the same as the dimension of all of M times 3P naught. And by the Riemann-Roch theorem, the degree of that divisor plus 1 minus G, and we know genus is 1. So it is 3 times M. So we know there are 3 M points consecutively. So it ends up at 3M minus 1. We have to count that 0 too. Okay. So what I'm saying is this SM, the level M of semigroup, is all the points, right? So I is 0, 1, the 3M minus 1. So this last point, 3M minus 1, should be one of the generators. There are infinite many generators. So this semigroup is not finite generated. So Dave Anderson wrote a paper, and he proved that when you have this nice situation, when the semigroup is finite generated, you can have a toric degeneration of your given variety with this variant line bundle. So this semigroup will achieve toric degeneration. This semigroup, no, of course not.
This semigroup what?
This semigroup gives us this toric degeneration of this.
Degeneration.
Yes. So toric degeneration of this embedded version. So you have a curve with the degree 3 in P2, and that semigroup tells you by choosing a certain term order of these coordinates, you will get this initial. So there are many versions. If that twisted cubic curve defined by ideal I, you can get an initial ideal. So by choosing some weight order, the initial ideal becomes a toric ideal. And this one, no, it does. I mean, it doesn't really say anything because we don't get finite generated algebra. In general, it's difficult. That's why these are the famous examples, right? And I think for the surface case, I think people completed the classification of these neutron Okounkov bodies. What kind of shape you may expect, and I'm still reading the paper.
People are working on it.
Yes, so the thing is,
This is only two-dimensional.
yeah, for surface.
We are two-dimensional.
Yes, I think yes. For each dimension, somehow I have to learn this like curve theory or the surface theory, and because it's all about the divisors for this variety.
So you said this is finitely generated, the level one. So it has it's a toric degeneration.
Yes, it gives you the
toric
toric.
degeneration. So you have a you have a toric manifold, toric variety, and there is a map, sequence of maps, or what?
Yes.
What do you mean by toric degeneration?
Yeah, toric degeneration can mean a lot of things, and for this case, for this one, what I mean by for this, the semigroup is generated by level 1. Yes. So let me put this X. So it's embedded, right? So let me use this Y as the image of X. Okay. Just the reason I'm distinguishing is that it works even when phi is not embedding. So we can talk about just the one inside of projective space. So why? So in this case, this is the zero locus of a certain ideal. It's a hypersurface. Actually, this is a principal ideal. Generated by a cubic homogeneous cubic polynomial. I don't remember. It really, what is this? It depends on how you will define the basis of this one. Okay. So that actually it will be y squared x minus 1, x minus lambda, something like that. Okay. Now, what it means is that there exists a certain weight order such that the initial ideal with respect to that, well, so let me put this. So this is, again, I don't remember F. I think F has 4 terms, and this initial ideal will be defined by 12 of these 2 terms. So this weight order picks up 2 terms. So it will be a binomial, which is irreducible. So this one is a toric ideal. It defines a toric variety.
So in other words, you can give certain toric structure on that image of this.
I see what I mean. There is a flat, one-dimensional flat family sequence, and then generic ones are our starting one, and the special one is a toric variety.
Okay, you have a one-parameter family of these embeddings.
Yeah, curves.
At certain points, it might be singular.
Yes.
But still, it is a toric.
Toric, yes, toric curve. Yes.
Can you? But you
Yeah.
don't know whether it is non-singular or not. The toric degeneration.
So it's case by case. So for example, for the flag variety, there's a well-known Gelfand-Zetley polytope. This one gives you this toric degeneration of a flag variety, and that toric variety is singular. So actually, that's what I'm going to do until the next week. Next lecture, Newton-Okounkov body of bott-samelson variety. So I will make clear what I mean by toric degeneration. So let me just introduce. I have 5 more minutes. Yeah. So right. So far we somehow glimpsed the introduction of Newton-Okounkov body theory. But I just want to point out. Of course, I'm still learning, but. I want you to keep in mind many papers are very technical because they want to use Newton-Okounkov body theory for their own goal. So there are lots of flexibilities, and so I try to sort of present this principal idea so you may improve. Well, I think I'm not in that status to give the advice, but that's my feeling from this 2 years research. Okay, so the last topic will be the Nobi of bott-samelson variety. Everyone knows what is bott-samelson variety actually. Professor Sa is an expert, so.
No.
So, well.
Bott-samelson variety is defined rather using, legal theory.
Yes. Okay, just to make things clear, let me write all this notation. So G is a reductive algebraic group. And H is a Cartan subgroup. So you can think of G is GLN or SLN. H is a diagonal matrices. And B is a Borel subgroup containing H. So B is upper triangular matrices. And you just denote alpha. Okay, so G is a reductive algebraic group of rank R. So let me denote alpha 1, alpha R as simple roots. Okay, so for me, in this case, alpha I is EI minus EI plus 1, where EI is the coordinate functions. And now let me use omega 1 to omega R as fundamental roots. Right, so for in this case, omega I is epsilon 1 plus epsilon I, EI. Okay, so that is just notation. Okay, now you just fix a sequence of simple roots. So let me just record this sequence of simple roots by the indices. Alpha I1, I1, IN. So sometimes I will just, so for example, I will just say alpha and beta. I will just choose 2 simple roots, alpha and beta. Sometimes I will just write down the indices. Sometimes I will write down the simple roots. Yes. Okay. Now, the bott-samelson variety with this I bott-samelson variety. Yes. So this is one of the definition, and so you consider this product. Okay, so this is minimal parabolic subgroups. Please let me know if there's any ambiguity of notation. And modify this Bn action here. The Bn acts on the right as follows. So P1, Pn, B1, Bn, P1, B1, B1 inverse, P2, B2, Pn minus 1 inverse, P2, Pn, Bn. Okay, so this is, so for this example, what I mean is the bott-samelson variety of alpha and beta is P alpha cross P beta modified by B2. Okay, sometimes we denote this one as P alpha, P beta modified by B, and have action B. Okay, so now so here are a few facts about bott-samelson variety. So it is a smooth algebraic variety of dimension n. So n is this number of simple roots I chose, and there is a morphism from bott-samelson variety to this flat variety, namely, so if I denote this one as equivalent using a representative, we just take the product of all of them. This is well-defined morphism, and if this I is a reduced word, then this mu is a birational morphism to the super variety. X omega, where W is just S alpha I1, S alpha IN. So in general, the super variety has singularity. So original motivation of this construction is that this is a desingularization of the super variety. And also you can understand this one as a P1 tower of P1 vibrations. So if you take this forced projection, P alpha mod B is isomorphic to P1. This vibration whose fiber is isomorphic to this last part, which is also P1. So in fact, if I choose these two roots the same, then the bott-samelson variety is isomorphic to P1 cross P1. So in this case, you get a toric variety. But bott-samelson variety is in general not toric variety. So let me just finish by presenting our question, main question, actually the question, and the idea. So what is an OB of BSI? So from now on, whenever say I write I, we chose I. Okay. Well, to answer to this question, we need a line bundle and an optimizable flag. Well, of course, you can find another evaluation. Next time, I will show you a certain expression of this line bundle on the bott-samelson variety. And main idea. So next time, I will make this idea precise. Main idea to find out Newton-Okounkov body of bott-samelson is as follows. So you have bott-samelson variety and a given line bundle. Next time I will tell you what it means. It's a line bundle. And you degenerate this idea to a certain bott tower. So what I mean is a toric variety, a line bundle on this toric variety, but one of the contribution by Megumi and myself is we got a very explicit description of this divisor D. So we chose a very explicit D, which describe this degeneration. So this degeneration is done by Grasberg, Karlsson in this differential geometry approach, and then later Pasquier described this one in algebraic geometry sense. Okay. So now in this situation, when you have toric variety with this line bundle, there's a nice candidate for the Newton-Okounkov body, namely the Newton polytope. Yes? So you may add, can you have this one as a Newton-Okounkov body of bott-samelson variety with a certain choice of flag? And the answer is yes, if this D, or the line bundle, degenerated line bundle E is base 0.3, then Newton-Okounkov body of a bott-samelson variety with this line bundle with a certain, there exists a flag, that's the statement. There exists a certain flag, optimizable flag, such that the Newton-Okounkov body is this Newton polytope. Okay, base 0.3 means this line bundle, for any point there is a non-zero section. Non-zero section which does not vanish on that point. So you can understand that way in terms of line bundle. The whole point is that this is very, very easy to check. This is very, very easy to check. And then D has an explicit description. So this gives you a very simple way to construct a one Newton-Okounkov body of bott-samelson variety. And if D is actually ample, this Newton polytope is actually a cube, combinatorially isomorphic to a certain cube. So that
D is what?
if D is ample or very ample, the same thing in this case, then this one is nothing but this cube, combinatorial cube, which means the toric variety is non-singular. So my second project is this algorithm somehow shows us this toric desingularization of this toric variety, which appears as this toric degeneration of a flag variety. So flag variety degenerated to a toric variety, which is described by Gelfand-Jetelny polytope, which is always singular. And this approach with certain nice assumption gives you a nice toric desingularization. So next time we will. Next time is basically I will make this degeneration and this assumption, this claim precise. Yes. Any questions?